Hello everyone, my name is Yash Patel, and this is my Lab 5 where I chose my own adventure as tracking the motion of a falling Slinky. So the procedure and goals. So for this experiment, the motion of a Slinky was observed falling down, and we generated two different position versus time graphs. One we got from Tracker, and the other one we got from our GlowScript computational model. So the goal of this experiment was to determine the effects of gravity and drag on the motion of a Slinky, and use this information to predict the motion using a computational model through GlowScript. And on the right, you can see the principles that were used for this model. So first we used Newton's second law, which includes the position update formula and the velocity update formula. We also used weight force and drag force, and you can see the formulas underneath the labels there. So this is the data and measurements from Tracker. On the left, you can see the Tracker recording. And we know that the mass of the Slinky is 0.204 kilograms, and we know that it initially starts just at the zero vector. So I calibrated the y-axis and x-axis so that it starts at the bottom of the Slinky. And then the final position is negative 0.4790, and this is at frame 677. And we recorded this, or this was recorded on a low speed camera, which records 300 frames per second. So that's why the gap between the frames is so large. And also calibrated using Veritasium's height, which is the man standing on the left, and his height is 1.75 meters. So this is the code for the initial conditions. Again, we know that the ball's mass is 0.204 kilograms, and we got the initial position from Tracker, and we know that it starts at rest, so the initial velocity is just a zero vector. Then we have the time step, which we set to 0.01, and this is just how the while loop is going to update. And we have g equal to 9.8 because that is the acceleration due to gravity. And finally we have j hat and the proportionality constant for drag. And this was calculated through trial and error, and kind of finding out when the computational model's end position matches up with the observed end position. So this is the code for simulation, and this is part one. So I have two while loops. The first one is set to run until the top of the Slinky reaches the bottom. And so for this simulation, we have the force of tension is opposite and equal to gravity. So these forces just cancel out, which explains why the bottom of the Slinky would remain stationary. And we'll get more into that in the later slides. And we also have the velocity update and position update formulas. So this is part two. Now this is set to run until the last observation on Tracker. And for this, drag force is included because the Slinky as a whole is now moving down, and also weight force. And if we combine these, we get the net force. And again, velocity update and position update are both included. So this is what we got. So this is the model versus observed comparison. So on the right, you can see the graphs. So the model position lined up pretty well with the observed position, except during the middle part. So the first part of the graph is spot on because the bottom of the Slinky was stationary, so obviously this is going to match up the whole way through. But the variance can be attributed to error in the tracking points on Tracker or an error in calibration. So why does the bottom of the Slinky remain stationary? So the reason for this is the bottom of the Slinky initially remains stationary because the tension force of the Slinky, and remember, the Slinky is just essentially a large spring. So the tension force of the Slinky is equal to that of the force of gravity. So this means that the bottom of the Slinky is in static equilibrium, which is proved by Newton's second law, because the two forces acting on it, which is itself and gravity, are opposite and equal, which means that the bottom will remain stationary until the top reaches the bottom. And this was kind of the basis that we used for building our computational model. So that was it. Thank you so much for watching, and I hope this was informative.